Hi everyone. So in this talk, we are going to explore how we can implement hybrid approaches with neural sparse and dense vectors. I would like to introduce myself. I am Seema Saharan. I'm currently working as an SRE at Autodesk. I'm also a CNCF ambassador, AWS community builder for AI category, and I have been a public speaker for many conferences like KubeCon, NE, and CubeDay, PlatformCon, and various others. And also, I am really passionate about open source and giving back to the community since my college days. So I love contributing to that. And also, I organize some of the events for CNCG, AWS user group, and HashiCorp user group in India. My co-speaker is Aditya Soni. He couldn't join us, but he has a message for you all.
Hello, OpenSearch Economy Europe. This is Aditya Soni. I'm one of CNCF ambassador and a DevOps engineer. Currently, I'm working at Forrester. I had some visa issues, that's why I was not able to join you all. But don't worry, I have Seema there, so we will be having a talk on how you can build hybrid search on OpenSearch. So for this talk, we are using two things here. The first thing is the dense vector, and then we have neural sparse. So we have prepared a demo, slides and a lot of stuff for you. So yep, enjoy that. Have a great day.
All right, so let's talk about the roadmap that is included for this topic. First, we will explore traditional search method because that's really important to understand before jumping into the hybrid approaches. And then we will understand what is dense search. Next, we will understand neural sparse and how we combine both of the approaches and make it into a hybrid search, and how open source supports hybrid. And we have a demo and some of the key takeaways from this topic. And lastly, we will have some time for Q&A. So first, to understand the search approaches, we need to go back to the traditional approaches. That's Boolean search. Excuse me. So first is Boolean search, where it's just like a keyword searching. There is no ranking, there is no nuance, and it is very difficult for user to be familiar with the query logic, and you can consider it as a Command F option that we use in our normal laptops, and it just searches for the particular keyword. So let's suppose I provided a keyword called car. It will only search for the occurrences, and it doesn't do anything else, basically. Next is TF-IDF, that is term frequency inverse diverse frequency, and basically it ranks all the documents and keywords by frequency, how much they are occurring in the documents and how rare is it. So how does it work is, let's suppose you have 10 documents and there is a word car occurring very frequently in a single document. Let's suppose it is occurring 20 times. So that rank will be higher. And if the same word, car, is occurring multiple times, more than 50, 100 times, but it is present in separate documents, then it will be ranked lower. And there is also a case if a word is occurring rarely in all the documents, then also it will be ranked higher, but lower than the singular document frequency. But with this approach, still the algorithm doesn't understand the user intent. It doesn't understand the synonyms. If I say automobile, it doesn't understand that it's similar to car, and it doesn't return anything. And to improve this, we have BM25, that's best match 25, and it's also referred as OK API, Okapi, however you want to say that. And because it was ran on those systems first, that's why it's named as Okapi. And it improves TF-IDF by considering the term frequency, saturation, and the document length. And it is very precise for if you want to have exact keyword matches. So in this flow diagram, it's like user puts in a query, and it's also mentioning inverted index lookup. So if you don't know, invert index is like, so normally indexing is like 1, 2, 3, and then it stores all the information about the keywords, right? But in inverted lookup, inverted index lookup, how it stores the data is, it looks for a word like, this is a great day today in Amsterdam. So it will it will store all the keywords in the first column, and then it will searches for the document. Let's say it occurred in document 1 and 2. It will say this occurred in 1, 2, and like that for each keyword it will display which document the keyword is present in. And then it ranked the results based on BM25. So here is an example for classic search pipeline. So user puts in a query bank, and like I explained, inverted index will be updated for that, and it will give the results like river bank or financial bank. So if you notice, it is still returning just the keyword based on the keyword. It doesn't understand the semantic behind it. It doesn't understand the meaning that river and financial are completely different things. Yeah, I covered it. Okay, so there are some limitations of traditional search. First is no semantic understanding. In the previous example as well, you saw that it just basically looks for the keyword, but not the intent and the meaning behind that. And it doesn't understand the similar words. It fails to understand the synonyms. Like I previously mentioned, that car is not equal to automobile according to traditional searches, so it doesn't understand that. It doesn't have personalization. So let's suppose your application has thousands of users, and if you are using traditional search approaches, all your user will have the same output. So let's suppose they are searching for iPhone. They're gonna get the same exact results. It doesn't update according to the person's preferences. If they are interested in, let's say, iPhone 16 256 GB and maybe more than that, or they are interested in Pro versions of it or lower versions of it, it doesn't understand that, and it doesn't give us the personalization for that. And there are some relevance gaps as well. So it is due to strict keyword matching, and computational costs with BM25 are pretty higher, because in BM25 it works with large documents. So if your application has maybe thousands of documents, so that processing is gonna take a lot of computational costs and time as well, because it's gonna search in each individual document. So it can be pretty expensive for large data sets. Now let's understand what are dense vectors. So they are compact, continuous array of numbers generated by neural networks to represent the meaning of text, images, and other data. And dense vectors are mostly non-zeros. As the name suggests, vectors. So we have we rarely see zero values with it, but in BM25 cases we see mostly they are zeros. And with dense vectors, we can have semantic relationship in low dimensional spaces. For example, in BERT, we have 768 dimensions. Dimensions means how many vectors are going to be created in a single document. So if you are using dense vectors in a single document for a single keyword search, it's going to create 768 vectors, and then it's going to use the other approach that we'll talk about and give you the results. And these vectors enable semantic search. So since it is it knows the meaning of the words, and it can relate to the synonyms as well. It just doesn't understand just not the keywords, but it understands the context behind it, and it can also result in a similar words as well. So with dense vectors, we can solve the issues that we had with BM25 and TF-IDF and all the traditional approaches, and we can rectify that here. So how does dense vector search work? So user inputs a sentence, and it goes into an embedding model, let's say BERT or any other embedding model that you can use. And dense vector captures a sentence's meaning and not just a keyword search, right? And it uses ANN search, that is approximate nearest neighbor search, and it gives us the semantically similar results. Okay, so for example, user puts in a query called affordable running shoes that we mostly use it in, let's say, e-commerce websites, right? If your e-commerce is still using traditional approaches, it will look for the exact keywords like shoes, even if it's irrelevant. It can be normal shoes. It can't understand sneakers or similar words, right? And with dense vectors, since we have the embedding model, and it will convert this query to vectors, and if you're using BERT, it will convert them into 768 vectors, and then ANN will find the product descriptions, and it will also look for the similar keywords like budget-friendly sneakers. And even if we don't have the exact query, affordable running shoes, it will still give us what the user wants, what the user is looking for. So there are some differences between dense versus traditional search. First is representation. So dense vectors are normally low dimensional, all are non-zeros. And with traditional, it's highly dimensional and mostly zeros. Does dense vector captures meanings? Yes, because it's also using semantic search. But with traditional, that's the biggest limitation for traditional search. So it just looks for the keywords that the document has. Then comes the synonym handling. Dense vectors handles that, traditional doesn't. Context awareness, that's the biggest use case is like e-commerce website. So it doesn't, dense vector understands that, traditional doesn't. And precision on rare terms. Since dense vectors highly rely on like context and semantics, right? It can sometimes miss if we are providing a rare term that's not present in the document. But with traditional search, since it's a straightforward keyword searching, it will return the correct keyword. Next is interpretability. For dense search, it's pretty low because it's kind of a black box for us. It doesn't have, so we don't exactly know what dense search gonna return to us and why did it return that particular keyword or result. But with traditional, it's each term is visible. Next is latency or resources. For dense, it's higher because it's using like vector search, and vector search are since it will create many vectors, it can be higher latency. And for traditional inverted index is pretty faster compared to dense search, so the latency is going to be lower. So let's say this is a similar example. So how dense search is handling this is user puts in a query car, sparse, like BM25 is basically token versus weight, and it's going to search for car and automobile, and dense search will convert them into vectors. So BM25 only matches car, but dense vector understands all the synonyms for the particular keyword, and it's going to return the same thing. But dense does not mean it's always better. Due to latency issues, since ANN search is highly computational and especially at scale, so if you're running maybe your documents are in terabytes, petabytes, it's going to take a longer time to give us the results back, and your search can go into hallucinations as well, and it can return semantically similar but factually incorrect results. So sometimes like you might have faced this issue that you want to search for something in your e-commerce website, right? But it's just not understanding what you want. It's just again and again repeating the same results, and it's not what you want. So you just get frustrated and move to the next e-commerce because we have so many. And it misses rare and exact terms. So dense vectors can overlook rare or domain-specific keywords critical in e-commerce or legal search. Interpretability, it's hard to explain why a result was returned because it's kind of a black box, like I mentioned, for dense search. So I have mentioned for e-commerce and legal documents, so user searches for a specific product or rare brand. It can be a new one, right? It's just a startup and they added their products on a famous e-commerce website, and they are not exactly returning the right products, but it's just returning all the famous ones in the first few pages, and it can miss exact matches as well. For legal documents, precise legal terms or citations may be overlooked if they are rare or not semantically close to the query, and it's really crucial to have the right results for legal documents. E-commerce, for a second, we can have like, okay, I can try maybe a different word, but for legal documents, it has to be precise. Now, understanding neural sparse search. A method where text is encoded into sparse vectors, only a few important tokens are assigned weights, making it easy to spot which words matter the most. So the neural search is like, let's say your user has given a sentence, right? And it doesn't always care for all the words in the sentence, but if your user query is important, has a few keywords that are really important, it will assign the weights to it. And the higher the weight, the more important the word is. It highlights key terms instead of hiding meaning, indents numbers, assigns clear importance to each selected token based on relevance. So this is an example flow diagram how neural sparse vectors work. So user inputs a query, we can use any neural model, for example, SPLAD, and it basically converts them into sparse vectors. Sparse vector is nothing but token weight, and based on the query and documentation, it converts into sparse vectors, and it uses inverted index lookup, and this results in fast search retrieval. So an example query is, we are using the same queries, affordable running shoes. So in this, if you notice, the keywords are assigned a particular number, right? So affordable is 2.1, running 3.4, shoes 4.7, like that. So based on this, like shoes is the highest weighted keyword. And if you notice that in this, only a few tokens have non-zero. So if we go back to the BM25, mostly of the results are zeros. Here, since it's converted into sparse vectors, and vectors are rarely zero in value, so we will only see the weights to it. And the model may expand the query with related terms and assign them appropriate weights. So you can use any model with this. You can use any maybe open source model like on Hugging Face or OpenAI or anything. But again, sparse individually is not always better because it misses deep semantics. While it was able to understand the queries and assign the importance to the keywords, but it doesn't really understand the semantics behind the keywords like dense vector did. And again, rare term handling is they are really strong at that, but it may struggle with the context and paraphrase beyond direct token expansion. And latency and scalability, since it's also using inverted index lookup, which is very fast compared to the normal search algorithm, but it's still, if we expand the data and we have a larger data, if we want to scale it, it's gonna take some time to get those results. So here comes the hybrid search, which is best of both worlds. A search method that blends sparse, that was focused on keyword, and dense, that was focused on semantics, the context behind it, and that looks up for the synonyms as well and understand what the user is asking. If we combine both of them, we can get precise and context-aware results. Processes queries with both methods, then merges and re-rank results. Maximizes exact matches and deep semantic understanding together. So, okay, some of the benefits of hybrid search are precision and context. Since we are combining sparse vectors and sparse as in neural search sparse and dense vectors, with sparse vectors, there comes a benefit of ensuring that we have the exact keyword results, and it also results, also gives us the result for rare terms. That was not a good point in dense vectors. And with dense vectors, it captures the meaning and context, retrieving relevant results when querying documents use different words. Next is improved relevance. So with hybrid search, it bridges the gap between literal search, literal keyword matching, and semantic similarity, ensuring users get the most relevant results whether or not their query is matching or not, because it can be really frustrating when a user doesn't get what they want on a search engine, or it sometimes is very frustrating in Google as well, because we are searching for something and it just hallucinates sometimes. And same with, I think sometimes ChatGPT also does that. So it goes in a loop and returns the same thing, and we have to we have to tell them the exact thing that we are looking for. Next is versatility, handles diverse data types and user intents, making it suitable for e-commerce, legal, support, and more use cases. It also enhances the user experience, because without users, your website is not going to survive, right? So we have to really focus on our user experience, and with this hybrid approach, we can achieve that. So with hybrid search, how it will work is user puts in a query. Okay, there is an arrow missing. So user puts in a query, and it will combine neural sparse and dense vector, and neural sparse will convert them into sparse vectors, that is token versus weights, and dense vector will be converted into dense indexes, embedding, and it will merge those results and give us the final ranked results that are the most appropriate results after the user puts in the query. So again, the same example, user puts in a query, affordable running shoes, and with neural sparse, it will return something like affordable. Basically, it will assign all the weights to individual keyword, and with dense vector, it will create it into a vector form, and it's called semantic embedding. And after the retrieval, sparse index will find the strongest keyword matches, like cheap sneakers, and dense will find the words that are similar to it, that are like budget-friendly trainers or something like that. And after this, with hybrid, we will get the most appropriate result for the user query. Now, with this, there are still some challenges. So first is score normalization. Sparse and dense scores have different scales. Combining them meaningfully is not trivial. Index complexities. Definitely, managing 2 or more indexes is it's really hard, and it's harder to synchronize the data as well. Next is latency. Parallel retrieval and fusion can increase response time if not optimized. So definitely, because most of the e-commerce websites runs on a larger scale, and we have a lot of data, right? So if you are putting 2 approaches parallelly, it will increase the overhead definitely. So depending on your use case, you can do both, but it really depends. You can also opt for one approach as well. But mostly, I think dense vectors are more appropriate if your user base are not, you mostly care about latency. Next is parameter tuning, finding the right balance between sparse and dense contributions for your domain. So how OpenSearch helps in hybrid search implementation? That's the main question here. And it supports hybrid queries. So first, you can start like this. So first, you can create the dense vector searches, and then compare it to neural search as well. So if you see a difference, then you can decide for your particular use case which one is better. And if combining both of them results in a better results, so you can use that as well. Next is score fusion tools. So it provides built-in score normalization and fusion strategies. Flexible indexing lets you store both sparse and dense vector per document. With OpenSearch, it becomes really easy in maintaining multiple indices as well. Scalability, it is designed for large-scale enterprise-grade search with hybrid vector support. So in the demo right now, I'm going to be showing you on a local system, but you can also achieve the same results on AWS and enterprise version of it as well. Let me, okay. So okay, so basically right now I am in dev tools in OpenSearch. I hope it's visible. Okay, so the first query is like by default, they when you create an OpenSearch dashboard and you go to dev tools, it's gonna be there by default, and you can just see if it's returning something or not, whatever data you have stored here, or if it's returning that or not. Next is we're gonna implement some settings. So we are putting these settings. So OpenSearch uses ML Commons library, and with these settings, we can run the ML models. All right. So here, for this part, I'm using a neural sparse model that is already present on the OpenSearch documentation. Let me, okay. So if you go here and search for pre-trained models, you can get those, and there are multiple, but I have used the sparse encoding so that it's easier since they already come with a pre-trained model, and I have just used the I think the first one. And if you click on config URL, you're gonna see this JSON file that I have put it here. And I'm going to deploy this to my OpenSearch. Okay, so now this task ID is important so that we can track if it's deployed successfully or not. So next, I'm checking the status of my task. I'm going to update this task ID. So it is created. Function name is sparse, and also, I would like to mention that model task type is sparse encoding, and format is torch, and you can see all the information about this model basically. Next is I'm going to create an ingest pipeline to create vector embedding. So if you, okay, so since I checked this, I forgot that I have to get the model ID. From where you can get is, you can just go here to the machine learning tab. If I refresh, the latest one should be, I think, this one, or I can just do get as well. Yep. So this is our model ID. We can also confirm here if it's present. Okay. So you can also get a list of all your models that has been deployed to OpenSearch, and you can get the details like if it's responding or not, and like basic details you can get it, and the status should be in responding state. So now that we got our model ID, I'm going to update this, and I'm going to create an ingest pipeline for this. So if it returns acknowledge true, that means it's successful. Okay. So next is, since I'm using like Amazon, you can name it anything you want here. This name can be anything. So I'm just creating an index with above ingested pipeline, and I think it's already present. So we can see the error resource already exists. So I'm just gonna name it like 2, and it will be the index neural search PQA Amazon 2 is created now. And if you notice that it is using KNN vector and the dimensions are 768, that means it's going to create 768 vectors. And let me get the model ID and update it here. So here we will see like it's proper, the ML model that we just created is properly deployed. And since I update this, it's gonna be 2. So basically it's working fine now. And I can, since it's a neural sparse search, we can ask it anything, but it can also depend on the your use case. So right now I'm just asking, tell me about the Amsterdam weather today, and it's gonna return. So it's basically searching for all the keywords, and it's assigning the weights. And if you see, there is Festival, Holland, and Amsterdam. If you notice, it's the weight assigned is 3 point something, which is the highest in all of the results. So it is able to detect the word in a sentence, right? And we can also, I already have some data passed in my OpenSearch. I think I can do 2. Okay. Okay, oh. Okay, I'm not sure what that is. I have to debug this, but yeah, this is about the neural search. So if you consider the dense search, so dense search is pretty straightforward. I used a Hugging Face model, and I'm using text embedding because that is by default. And for neural sparse, it's generally this one. This neural will be for the neural one. So you can add both of these in your JSON file in DevTools and search based on that. Yeah, so let me go back quickly. Present. Okay, so some of the key takeaways from this is hybrid search is it's a strategic bridge to GenAI. It's easier to entry point for AI enhanced search, and OpenSearch simplifies this approach. It's in a quick way, and we can use multiple models as well. So we can combine multiple models. Like it doesn't have to be a single model. So multi-models are basically supported. And hybrid search isn't just an upgrade, it's a strategic stepping stone to AI-driven search experiences. Yeah, and you can connect with me or Aditya here, and we can discuss more about it and how we can improve this hybrid approach. Thank you.
Do you want to have a question from the audience?
Yeah.
We don't have so much time, but at least one question would be maybe allowed. Does anyone has a question? Otherwise, you can talk with her after the talk. We have one question.
Okay, you mentioned that the sparse search does not capture very deep semantic meanings, and is there any example for you to showcase that hybrid search is better than the semantics, the sparse search?
Okay. Okay. I have basically just prepared a POC on it. So I haven't went on deep level. So maybe I will check on that and get back to you. Yeah.
Thank you so much for your talk.
Thank you.
Applause. Thank you.